if we have the function f of xy equals 2x squared plus 3y squared, we can look at its contour lines, the contour lines of its graph. Its graph is going to consist of points in three-dimensional space. We're going to let z equal f of xy, so we have z equals 2x squared plus 3y squared. That is going to give us an elliptical paraboloid, okay? And we can recognize that as a simple quadratic surface, and I wanted to start off with a pretty simple idea, simple surface, okay? Now, we want to look at the intersections of this paraboloid with different planes parallel to the xy plane, because if you imagine this as a set of hills, or that's actually a paraboloid, okay. Cut the paraboloid at different levels, you get ellipses, and the ellipses change size. The paraboloid gets bigger as you move up the z-axis. It expands in this direction. So you're going to get bigger and bigger ellipses as you move upward and intersect this graph with planes where z equals constant. So in the plane z equals 0, for example, well, the only point that satisfies this equation when z equals 0 is the point 0, 0, 0. So we start at 0, 0, 0, and we recognize that as the vertex of our paraboloid. In the plane z equals 1, what do we get? We have 1 equals 2x squared plus 3y squared. That's what? That's an ellipse. We could put it in standard form. X squared over 1/2 plus y squared over 1/3 equals 1. Yeah, and I did that right. It's been a few days since I did that, and I just want to check my arithmetic here. Okay, so in this case then, your denominator, x squared over 1/2, is the same as x squared over the square root of 1/2 squared. The square root of 1/2 is therefore your semi-axis in the x direction, and of course the square root of 1/2 is square root of 2 over 2. So we can write this ellipse in this form and see that our semi-major axes are square root of 3 over 3 on the y-axis, square root of 2 over 2 on the x-axis. Again, again, something like 3y squared is y squared over 1/3, which is y squared over the square root of 1/3 squared, and the square root of 1/3 is square root of 3 over 3. Okay, that's not the point. The arithmetic isn't the point here, but we want to try to maybe be clear on it. Okay, so that's the z equals 1 ellipse. Okay, we could do the z equals 2 ellipse. Okay, and I didn't do it, but the z equals 2 ellipse, well, we'd have 2 equal to this. We'd have to divide through by 2 to get the ellipse in standard form. We have x squared over a squared plus y squared over b squared equals 1 and all that stuff, which I have to assume you can do. And we would then end up with just x squared plus what? Y squared over 2/3. And semi-axes of then 1 and the square root of 2/3. Okay, which is, yeah, you can write it out. So in general, the ellipse that we get when z equals c, where c is any number that works up here, which would be any non-negative number, the semi-axes turn out then to be square root of 3 over 3 times the square root of c. That would be in the y direction. Square root of 2 over 2 times the square root of c in the x direction. So that our picture of the semi-axes for c equal 1 to 4, okay, well, when c equals 1, we'll get an ellipse with these semi-axes. Okay, for c equals 2, we get ellipses where the semi-axes are square root of 2 times greater. because of the square root of c thing here. By the time we get out to c equals 4, the semi-axes are twice as big as they were for c equals 1. So at c equals 4, we get this. C equals 2 and 3, we're in between here. And these distances are actually decreasing. Okay, the changes in the lengths of our semi-axes decrease with every integer increase in c because the square root of c decreases. It changes by a decreasing amount as c increases by successive positive integers. By the time we're out to c equals 9, we will have tripled our semi-axes here and here. And we'll have 4 contour lines corresponding to c equals 5, 6, 7, and 8 between the c equals 4 and the c equals 9. If we went out to c equals 16, well, there's 7 integers between 9 and 16. We'll have the c equals 16 semi-axis out here. Another step, okay, step being this distance here. And we'll have 6 additional lines in the same distance as we had the 4 additional lines here, or the 2 additional lines here. Okay, so you can see that these contour lines are going to be bunching up considerably. Okay, so contour lines for c equals 1, 2, etc. progressively bunch up, but there's no limit to how big they can get. It's just they get closer and closer together, which just indicates that you have to move out by less and less in the xy plane to get a z value that's 1 greater. And that comes about because the parabola is increasing in its z value at an increasing rate as you move away from the axis. That's a little vague, but if you know how to read a contour map, you see that this kind of a contour map shows you something that's getting steeper and steeper and steeper. More closely spaced contour lines tell you that things are getting steeper. Now, if we had, by contrast, z squared equals 2x squared plus 3y squared, instead of z equals 2x squared plus 3y squared, then our z equals c contour line, you can see pretty easily, will have semi-axes square root of 3 over 3c, square root of 2 over 2c. Okay, because z being equal to c, z squared is going to be equal to c squared. When we divide over here by c squared to get the 1 over here, our denominator will increase by the factor c. So that we get equally spaced contour lines. They don't bunch up. Now, what does it look like if instead of bunching up contour lines, which give us this shape, what happens if our contour lines maintain equal spacing? Well, that means every time we go up 1 unit, the ellipse grows by the same amount. So we go up another unit, grows by the same amount, same amount. Think about that until you're convinced that that's the description of a cone, an elliptical cone. And I didn't write that down here, but it's worth writing down. And of course, it's not difficult to establish that this quadratic surface is a cone. Also, it extends both above and below the axis. It's a cone that comes to a point at the origin and then expands again down below the xy plane. Now, we've looked at what happens if z equals 2x squared plus 3y squared, z squared equals 2x squared plus 3y squared. What happens if z cubed equals 2x squared plus 3y squared? Well, in this case, for z equals c, we get an ellipse with semi-axes in the same ratio, but with the square root of 3 over 3 and square root of 2 over 2 both multiplied by c to the 3 halves. Now, what does that do to our contour lines?